Namaskaram. Welcome to another video of GPU programming with Mojo. I'll take this opportunity to wish each and every one of you a happy new year. Hope all your desires come true. And if the desire especially is to write the next generation AI and GPU applications, you're definitely invested in the right stack, in the right language, in the right framework to make that happen. Mojo as a language and Max as a framework had a great momentum in 2025. And I see that not stopping in 2026. In fact, in a few years, it'll probably revolutionize how we write AI frameworks and applications. Now, speaking of AI applications, one of the most fundamental operations that exists is matrix multiplication. It sort of constitutes 85% of all AI computations in any architecture, in any model. So by ensuring that we optimize matrix multiplication, especially on GPUs, we sort of help the AI applications and the AI frameworks perform better. That's why it's still a hot area of research, both at the software level to find out the best algorithm to do that, as well as from a hardware perspective to ensure we provide the right hardware wiring to make the computation faster. So today we'll explore some of the primitives that Mojo provides to make this a very performant kernel when using matrix multiplication. The matrix multiplication itself is a simple operation where you take a row from matrix A and multiply with column B from matrix B. You continue that for all columns, and once you exhaust the columns, you shift to the next row and repeat from column 0 to the length of all the columns inward, each time producing a single output. The key observation here is that every operation which is multiplying a row with a column is independent of the other operations, meaning if you are multiplying row 1 with column 1, it's independent of row 1 and column 2. The first operation is not deciding or affecting how the second operation should be performed, which means they are mutually exclusive, hence can be performed in parallel, which is where GPUs shine. So with that background in mind, let's look at the implementation and see how we can leverage this and some of the inbuilt primitives that Mojo provides to make and write a very performant matrix multiplier. The setup for today's video would be to take a 9x9 matrix and multiply to produce an output which has 81 elements. The block size is considered to be 3x3 in 2 directions, and the threads per block is 3. So the implementation you see on the screen is a native matrix multiplication where you just take a row and column and write a simple loop to show the multiplication. So we grab the thread index, the global index in the y direction, which is the row. We take the global index of a thread in the x direction, which is the column, and we write a simple loop which fixates the row and changes the column, multiplied by fixates the column and multiplies the row or increases the row. So essentially we are trying to do this where we fixate the row, proceed in the column, fixate the column and go down for all the rows and produce an element. Since each thread is doing this operation, there are about 81 threads involved performing 81 operations to produce an output vector of 81 elements, which is in itself is very parallel and performant compared to a CPU version where you have to write a loop. The second advantage, which is a hidden advantage which we didn't speak about in the earlier videos, is something called a decorator such as @parameter. What this does is, if you tell the compiler how many iterations you'll be performing, in our case we know it's 9 because there are 9 rows and 9 columns. If you give a hint as to how many iterations the loop will perform beforehand, it can do what's called as unrolling. It sort of arranges the instructions in the assembly language in a way it's not in a form of a loop, but is in a form of a straight line. Anytime a loop is involved, the compiler has to check, the hardware has to check, and it causes some sort of a friction, meaning it takes that extra milliseconds to verify and then compute. Whereas if you let the instructions be in a straight line, it bypasses the checks and executes them in a linear fashion, hence the execution is much faster. So any check is like a stop sign. You have to stop, verify, and then take a turn. Whereas it's easier to drive a vehicle down the line without any such restrictions, and hence it'll be much faster. So adding just a simple decorator like this, when you know the compile time parameter, uh, gives you a great boost in your programs. Now we want to take this up a notch and see if we can further optimize the matrix multiplier. Now instead of grabbing one element from each row and multiplying with an element from another matrix, we want to grab a group of elements, which in the GPU world is referred to as a tile. The group is in a form of a square and hence looks like a tile, and hence we call it a GPU tile. So essentially we are breaking down our matrix multiplication into smaller chunks, and we want to use the smaller chunks to our benefit, use some of the hardware elements to make this faster. Before we go into the implementation, let's look at the visual to see how it's done, and then we can understand the code better. We'll open up the algo visualizer. So this is our starting setup, 81 elements, 2 matrices. What we do is we sort of pick our tile size to be 3 by 3, and we start with not with one element of matrix A and multiply with one element of matrix B. Instead we grab a bunch in here meaning 3 by 3, which is 9. Then we first place them in the shared memory. So we create a shared memory and place it there. In the shared memory, we perform the operation. That results in an output, which is not the final output for this specific row. If you are considering the tile to be one row here, it's not the final product, but rather a partial one. You let the column step one down below, and you have the row go shift one to the right. And finally, you finish the operation producing the output. So essentially you're increasing the scope of your multiplication, not just to one, but a group of elements. And this is done to take advantage of the shared memory, which is tiny but really fast in its computation, because it's the closest memory to thread. So you want to grab a small chunk from the big global memory, drop it in shared memory, and do it. So that is the advantage of having a tiled matrix multiplication. But there is a hidden advantage. If you tell there is a tile, and if you break it down into a bunch of elements, it sort of instructs the compiler that there is further elements down the line, which the compiler sort of gets a hint when you mention the word tile, or rather you simulate the concept of tile in your program. It hints the compiler that there are elements to be processed in the future. When you process the first tile, it knows there are 3 tiles. So hence it sort of puts the data from global memory onto a cache. So you don't have to go to cache and fetch every time. You don't have to go to global memory and fetch every time. You go to the cache and fetch the subsequent elements after the first tile is done. So in a way, sorts of, makes the process go faster. But there is the secondary advantage. Mojo also provides a tile API. So you don't have to write a loop to fetch a group of 9 elements as we have done here. You could, but you can also use a built-in API called tile that grabs the elements by itself and produces the result. That's one advantage by using the concept of tile. The second advantage we see in the diagram is copying from the global memory to shared memory. Mojo also provides a primitive called copy SRAM to DRAM, which helps in the copy process. So let's shift over to the code and see how that looks like. So here we see a naive implementation where we use a shared memory. We grab, in this case, 3 tiles. We copy it to a corresponding shared memory. All this is just specifying the tile start, and the offset so that you grab 3 by 3 and drop it in shared memory. Finally, within the shared memory, it's a simple matrix multiplication as you have seen above with the decorator, so that you unroll and take advantage of the benefits the compiler is able to provide. You write them back to the output. But as I said, the Mojo also provides what's called as a tile API. So you don't have to write a specific code to copy this tile. It gives you a tile API, which you can say 3 by 3, and it will fetch the 3 by 3 block for you. So which is the first advantage, make use of inbuilt to grab a group of elements. The second advantage is it gives you an inbuilt function called copy DRAM to SRAM. This function is responsible for copying from global memory to shared memory, which you have done in the earlier videos, and we have also done this in the prior example. But the advantage of this built-in function is many. First, when we do it, it goes from RAM to register and then to a shared RAM. So there's an intermediate step. Here it bypasses the registers and goes directly to shared RAM. Obviously, skipping a step is much faster. The key word here also is async. So as the first set of data is getting copied over, it brings the second set immediately. So it doesn't let the GPU wait even for a second or even for a few nanoseconds. It keeps feeding the execution cycle so as to not to make it wait. So hence the async is very important, and this copy function enables us to do so. Finally, it doesn't grab one element. Even when it grabs a tile, it doesn't grab one element. It grabs row by row. So this copy function, which copies from global to shared, doesn't work element by element, but rather works row by row. This is configurable, but by default it's row by row, which then helps you to copy it faster. So not only does it bypass the register, not only does it become async, which keeps feeding the execution cycle, but it also grabs multiple elements at once. All of which helps us make the copy operation really fast. And then since there is a built-in function, your code doesn't have to check for boundary conditions and do all the math, and so it looks a lot cleaner. So our tiled implementation from a naive one, where we have to ensure we copy it to a shared memory, we set the barrier, we do the matrix multiplication. Here we skip and we use a tile API. We still have to create the shared space, but the copy operation itself is done through a built-in function. And one of the parameters for the built-in function is the layout, which we say copy row wise, which is copy 1 by 3, which is copy 3 at a time. You can say 2 rows at a time or 3 rows at a time, however you see fit, but by default it's 1 row at a time. Hence ensuring not only are you using tile API, which is efficient to copy a tile of elements, you're also making the copy operation more efficient, both of which gives you an enormous boost in performance. Finally, the add parameter still does the same thing, which is unrolling the loop and gives you a compiled hardware or compile time benefits that we saw in the first example. The rest of the code is just setting up the input vectors and running the program to produce the output. So we see in this, the key takeaways are, anytime a compile parameter is known, use that for your advantage, especially when the loop is involved. Second, whenever there is an element involved, think about whether you can bring the whole tile and take advantage of tile API from Mojo. Whenever there's a copy operation from global to shared memory, try to use a built-in function which provides all the benefits we talked about, which is async, bypassing the registers, and grabbing multiple datas at once. These steps alone takes you from a basic GPU programmer to sort of a intermediate / advanced programmer, because these are the techniques used in many GPU programs to make it more efficient, especially in the field of AI. I hope this gave you a sneak preview as to how matrix multiplication is fine-tuned to become more performant. It's not the end all be all because there are certain refinements with respect to register tiling and swizzling, which we'll talk about in the future videos. Thanks for listening. Have a nice day.